Okay, so this talk is about sketching for first order method, efficient algorithm for low bandwidth channel and vulnerability. Uh, this is a joint work with Zhao in Taiwan, Zheng and myself, and this paper is in ICML 2023. So the problem we study here is a standard problem called federated learning. So this is a very popular distributed learning scheme. The idea is think of you have a global loss function f of w. It is a sum. It is an average of n different local loss function fc of w. And here n denotes the number of clients or the number of local machines. And we assume we have a central server to coordinate across all the local machines. And the key idea of the federated learning is that each client, they have local and private data. They do not want to review this private data to the central server. So what they do here is they say, instead of sending you the private data that I care about, I instead compute a gradient with respect to my local data. And the hope is by only computing a gradient, it effectively hides the privacy of the stuff I care about. Um, as you can imagine, for such a distributed learning scheme, it is very important to get an algorithm with a good communication cost because let's say if your local client is your cell phone, then it is usually connected to a low bandwidth and unreliable Wi-Fi network. So it is essential to design algorithms that fits into the low bandwidth channel, which are usually the cases for the federated learning. So our solution here is based on sketching, very well known tool in numerical linear algebra. So consider this warm-up example. The loss function is just a linear regression. You have a design matrix, huge design matrix n by d, and the label y of size n. And for each local machine, it has a subset of rows of this matrix. So, and the loss is just the mean square loss. And for this case, what we do here using sketching is to sample a random matrix R of size B sketch by N, where B sketch is much smaller than N. And instead of solving this global objective, we multiplying this random matrix with this large matrix X, and we instead of solve this sketch regression problem. And this is a so-called sketch and solve paradigm. And one of the advantages of sketching is that the solve step, after we reducing the number of rows, is very simple. But we kind of overly simplify the problem here by only considering a linear regression, in which most of the modern machine learning models are much more complicated than that. So how do we handle such case when FW is very complicated and you cannot just solve it explicitly? The idea is instead of applying the sketching matrix to the entire problem, we apply the sketching matrix to first order information such as a gradient. This leads to our main algorithm. And before diving into that, we need to introduce some notions. So we call sketch as a mapping of a vector from R of D to R of B sketch, where B sketch is a parameter that we can control. And D sketch is a mapping that maps a vector in dimension R of B sketch back to R of D. The intuition is that the sketching operator compress the gradient information, and the dsketch operator extracts the gradient information by decompress the compressor vector. And the hope is if we compose the dsketch operator with a sketching operator, the result is very close to the vector that without any compression and sketching. This motivates us to consider the notion of coordinate-wise embedding introduced by Song and Yu. We say a randomized matrix R of size B by D from a distribution pi satisfy an A coordinate-wise embedding. If for any fixed vector G and H, we have that the inner product of sketch H and sketch G in expectation is unbiased estimator of H transpose G. And the variance of the sketch inner product is also very small. So we write here in terms of second moment. If you extract both sides by H transpose G square, then we get a variance bound, which is smaller than equal to A divided by B sketch times the norm square of these two vectors. Where does the name coordinate-wise come from? If we choose H to be the ith standard basis, then the condition reduces to that R transpose R of G is a vector G itself, and the norm of R transpose R of G square is less than or equal to 1 plus a small additive variance term of the norm of the vector G. Given this family of random matrices, then a good choice of the sketching and de-sketching operator is just when you want to sketch, you apply R to X. When you want to de-sketch, you apply the transpose R to X. If you recall the guarantees we have here, when you consider d-sketch applied to sketch, it's essentially this R transpose R operator. And we have that in expectation is unbiased, and it has a very small variance. The question is, does such distribution pi even exist? And a very important result is that many typical sketching matrices satisfy such a property with various values of A. And here is the main theorem for the coordinate-wise embedding sketches. If we set the sketching operator as R times X and d-sketch as R transpose X, where we choose a sequence of independent sketching matrices denoted by R of T, then these operators are independent of each other. And moreover, a very important and good structure we have is both of these operators are linear. And as you can see here, we have this unbiased estimator due to the R transpose R expectation property, and we have this bounded second moment property, where the variance term translates to this alpha parameter. And as you can see here, the alpha is A times B, D over B sketch, and for most of the popular sketching matrices, the parameter A is just a small constant. So you end up with O of D over B sketch. Given this sketch and de-sketch operator, we can design a framework for federated learning, which is effectively illustrated by this picture. So what do we do here? So during the initialization phase, we send random seeds of these random sketching matrices from the central server to all the local clients so that we can ensure at each iteration they use the same sketching matrix. And at each iteration, for what each machine do is they first download the parameters from the global central server, and then they do this step. They apply a d-sketch, the transpose of sketching operator, to this parameter, and it performs local gradient descent using this globally downloaded parameter. After perform this local gradient descent for k steps, what it does, it applies the sketching operators to this change, which can be viewed as like your initial weight vector from the central server. and the new vector you obtain after k iterations. And it sends this sketch changes. Um, I guess for the sake of discussion, think of this k as 1. So this is essentially sending the sketched gradient to the central server. And what the central server did is a simple average across all n different sketch gradients. And then it sends back the sketch gradients average to all the local machines and repeat. In terms of convergence, we can prove the convergence assuming the loss function is smooth and we have different bounds when the function is strongly convex or non-convex. And the bound is the SGD flavor of bound in the sense that you have a term which captures the geometric decay of the loss function, and you have another additive term which can be viewed as like a SGD style noise. And why do we have a SGD style bound here? It actually makes a lot of sense. If you think of SGD, you can think of you reduce the number of training samples to improve the training efficiency. And what we have done here is we reduce the dimension of vectors to improve the communication. So our method should be treated as a dual for the SGD algorithm. So how does this algorithm address the privacy issue? We have in our paper, we have shown that even with the randomized sketching applied to these gradients, this algorithm is not secure at all. In fact, it can be attacked by a very simple first order method, which is called gradient attack. And in our paper, we show that under mild assumptions on the loss functions, an attacker can probably recover the private local data just using gradient descent. So in order to protect the privacy, we need to use tools from differential privacy for provable guarantees. And for more details, please see our paper. And this list of references, and that's all. Thank you.